Hey, brothers and sisters, Doc Not here. Going to do another video for you for chemistry. I'm going to talk today about um, AMU versus the gram per mole versus and converting from mass of a compound to moles of a compound, and then using the stoichiometry of a reaction to convert from mass of one compound to the mass of another compound, or moles of a compound to moles or mass of another compound, and so forth. So today we're going to get into stoichiometry and some conversions from mass and moles. All right, let's go ahead and jump right in. Get to my camera here. There we go. All right. So I wanted to start off by talking a little bit about the difference between AMU, or U as it's now called, and the unit for grams per mole. So AMU, which is the atomic mass unit, is actually equal to 1.661 times 10 to the negative 24 grams. So it's a very small number, but it's just a mass, right? It's a very small mass. In fact, in reality, what this number is equal to is it's equal to 1 gram divided by Avogadro's number. We'll talk about Avogadro's number again in a little bit. So 1 gram then is equal to 6.022 times 10 to the 24th, 10 to the 23rd AMU, right? So this is Avogadro's number times AMU, atomic mass units. This again is Avogadro's number, right? So N sub A is equal to 6.022 times 10 to the 23rd. And that's just basically things. So that could be atoms, molecules, formula units, dollars, divided by mole. Okay, it's per mole, right? Basically, Avogadro's number is things per mole. Give it a S there. All right. So again, Avogadro's number is just a number, kind of like a dozen. You can have a dozen eggs, a dozen cars, a dozen whatever, right? That's just things per dozen, for in the case of a dozen. And then, so a gram is 6.022 times 10 to the 23rd AMU. And AMU is a very small unit of mass. And generally we use AMU to measure atoms or molecules, right? So we use the AMU to measure atoms or molecules. We use the gram to measure moles of atoms or molecules. Joules. There we go. I can't spell, but you get what I'm talking about, right? So when we're measuring moles of atoms or molecules or formula units or whatever, we usually measure in grams. When we're measuring just the one single atom or molecule, we'll use AMU, right? So that's the difference between those two. Okay, so with that under our belt, let's talk a little bit about how to convert a formula unit. So this would be a formula unit, right? It's a formula unit. It could be a molecule. It could be the formula unit for an ionic compound, whatever. But it's just some generic AB2, right? So if we have the mass of AB2, and that could be in AMU or grams, right? Whatever. And we want to convert from the mass of AB2 to moles of AB2, well, then we're going to need to use the molar mass of AB. Well, I'm having AB3 here for some reason, but AB2. Okay. So let's put the 2 there. There we go. Correct that. We'll just need the molar mass. And then so if we have the moles of AB2 and we want to convert to mass, we use the molar mass again to convert to mass. So between mass and moles, we always use the molar mass. To go between the number of units, formula units or whatever, we're going to use Avogadro's number. Okay, Avogadro's number. All right. So so that's how we do that. Let's look at a chemical about a chemical formula, or sorry, a chemical equation. So we have A2 plus B going to AB3. Okay, so A2 plus B going to AB3. This is not a balanced equation. You can tell because I have two A's here and only one A there. We have three B's here and only one B here, right? So what we're going to do is we're going to balance this first. So let's go ahead and balance the A's by putting a 2 here. And then that means we have 6 B's. So if we just put a 6 here, now our chemical equation is balanced, right? This is the reaction. It's balanced. And the stoichiometry is that there, for every A2, there are 6 B's, okay, that react with A2. And then for every A2, we make 2 AB3s. Okay, so one A2 reacts with 6 Bs to form 2 AB3s. That's our chemical reaction and the stoichiometry between them. Now, if we wanted to, if we were given the mass of A, right, we have a certain mass of this molecule, and we wanted to find out, let's say, what the mass of B we would need to have to react with it, then we would take the mass of A and convert it to moles. And to do that, we need to use the molar mass of A, and we'll use the molar mass to convert the mass from, and remember, molar mass is in grams per mole, right? And we would convert from mass, which is in grams, to moles, which is in moles. And then we can convert from moles of A to moles of B using the stoichiometry of the reaction here. In this particular case, we have one A2 for every 6 Bs, right? So we would use the ratio of 6B over A2, right? And that conversion factor then would be used to convert from moles of A to moles of B. Now, to convert from moles of B to mass of B, we'll use the molar mass, which again is in grams per mole of B. All right. Okay, so that's the theory. That's how we're going to do all this. Let's go ahead and do some problems here and figure this stuff out. All right. Excuse me. So we have the thermite reaction. Okay. The thermite reaction is used to create molten iron. For the following chemical reaction, calculate how many moles of aluminum oxide are formed from 8.921 grams of aluminum and excess iron 3 oxide. So here we have a chemical equation which is not balanced because we have 2 aluminums here, only 1 here, 2 irons here, and only 1 there. So we can just go ahead and put a 2 here to balance our aluminum. Put a 2 here to balance our irons, and actually everything is balanced out at this point, right? Okay, so so we have 8.921 grams of aluminum. So we'll just start with that. 8.921 grams of Al solid. Okay, we want to convert from grams of aluminum to moles of aluminum oxide. So we want moles of this, right? So what we're going to have to do is we're going to have to use our periodic table and find out what the molar mass of aluminum is. Well, if I look at my periodic table here, the molar mass of aluminum oxide, which is hard to see in my video, but it's 26.98. So this is going to be, multiply this by 1 mole of aluminum per 26.98 grams, right? And now we want to convert from moles of aluminum to moles of aluminum oxide. So we multiply this using, so what we did here is we used the molar mass, right? of aluminum to get to moles of aluminum. Now we want to go from moles of aluminum to moles of aluminum oxide, which in this case is our product. Okay. And we're going to use the mole ratio like we did here. Okay. But in this case, it's going to be 1 mole of Al2O3 for every 2 moles of aluminum. Okay, there's our ratio. So in this we only needed to go to moles. We did not need to go all the way to mass. So we're just going to go to moles here and stop. So let me get my calculator, which I should have gotten out earlier, but I did not. Okay. And we'll do our calculation. All right. So 8.921 divided by 26.98 and then divide again by 2 equals 1.653 times 10 to the negative 1. 1.653 times 10 to the negative 1 mole Al2O3. Okay, so there's the answer to the first part. Now the second part is asking how many grams of aluminum oxide are formed. So now we just need to conform. So now we're basically going through this last step here, right? So we take the 1.653 times 10 to the negative 1 mole of Al2O3, and we need to multiply it by its molar mass. So let's find the molar mass. The molar mass of aluminum oxide is going to be per mole of Al2O3. What we got to do is we take the molar mass of aluminum, and there's 2 aluminum, so it's 2 times 26.98 plus 3 times the molar mass of oxygen, which is 16.00, and we get 101.96 grams per mole. 101.96 grams per mole. So there's our molar mass. So we take the 1.65 times 10 to the negative 1, and we multiply that by 101.96, and we're going to get 16.82. 16.82 grams of Al2O3. So what we did was we went from the mass of aluminum to moles of aluminum. We did that here. And then we went from moles of aluminum to moles of aluminum oxide using the mole ratio from the chemical equation, right? And then we used the molar mass to go from moles of aluminum oxide to mass of aluminum oxide. Boom, we got our answer. Okay, so that's how we go from mass of of a reactant to the mass of a product. Let's go ahead and do another one here. Okay, so gaseous ammonia is formed from a reaction of nitrogen gas and hydrogen gas. What mass of nitrogen is needed to produce 15 grams of ammonia? All right. Well, what we have here is we have that gaseous ammonia is formed from the reaction of nitrogen gas and hydrogen gas. So we have nitrogen gas. Remember, that's a diatomic gas plus hydrogen gas, H2, also a diatomic gas, form ammonia, which has the chemical formula NH3, and that is also a gas. Okay, so we have 2 here, so let's put a 2 in front of that. That means we have 6 hydrogens, so that means we need a 3 there. Now here's our balanced chemical equation. We want to produce 15 grams of ammonia, right? So we'll start with 15.0 grams NH3. We're going to go from grams of ammonia to what it's asking for is what mass of nitrogen. So from grams of ammonia all the way to grams of nitrogen. Okay. So we'll take the mass of ammonia and we'll multiply it by 1 mole of ammonia, NH3, divided by the molar mass, which is going to be nitrogen is 14.01, and we have 2 of them times 2. No, sorry, times 1. We have 1 nitrogen in there, plus 3 times hydrogen, 1.008, gives us a molar mass of 17.03. 17.03 grams. Okay, so now our grams will cancel out. Now we're going to go from the mass of ammonia. Sorry, we just converted from mass of ammonia to moles of ammonia. We're going to go from moles of ammonia to moles of nitrogen. So the molar ratio that we want then is 1 and 2 for every 2 NH3. Okay, now we're in moles of nitrogen, but what the question asks for is what mass of nitrogen. So we need to use the molar mass of nitrogen. And so nitrogen is 2 times 14.01, and that's going to be 28.02. So that'd be 28.02 grams of nitrogen for every mole of nitrogen. So now we have grams cancel with grams, moles cancel with moles of ammonia, then moles of nitrogen cancel with moles of nitrogen. We're left in the mass of nitrogen. Okay, so we'll do this calculation here. 15 divided by 17.03 divided by 2 times 28.02 equals. So this is going to be 12.3 grams of nitrogen. 12.3 grams of nitrogen, which makes sense. If we're producing 15 grams of ammonia, most of that mass is going to be the nitrogen because hydrogen weighs so little, right? But some of that has to be made up of hydrogen. So there's our answer there. How about we do another one more, huh? Or I actually have a couple more on the next page. So let's do this. Zinc metal reacts with aqueous hydrochloric acid, HCl, to form aqueous zinc chloride and hydrogen gas. So we have zinc metal, Zn, solid, reacts with hydrochloric acid plus HCl, aqueous, to form zinc chloride. So you need to know how to make that formula. Zinc is a +2, chlorine is a -1, so it's going to be ZnCl2, and that's aqueous, right? So AQ plus hydrogen gas plus H2 gas. And it's important that you know that hydrogen is one of the diatomics. Okay, so here's our equation. We have 2 chlorines here, so let's put a 2 here. That balances the hydrogens as well, and the zinc is already balanced. So our chemical equation is now balanced. How many grams of zinc are needed to react completely with 12.5 grams of HCl? So we're going from mass of HCl to mass of zinc, okay? Which means we're going to have to go through moles to do that, right? So let's start off. We have 12.50 grams of HCl. In order to go from mass of HCl to moles, we need to use the molar mass of HCl. So Chlorine is 35.45. So there's one chlorine, 35.45 plus one hydrogen, 1.008 equals 36.46. So that'd be 1 mole HCl per 36.46 grams. So now we're in moles of HCl. We want to go to moles of zinc, right? So we multiply then by the ratio of 2 HCl's and 1 zinc. So 1 mole zinc for every 2 mole HCl, right? So grams HCl, mole HCl, mole HCl. We're in mole zincs now, right? So now we got to convert from mole of zinc to mass of zinc. We need to use the molar mass of zinc. So zinc is 65.38. So that's going to be 65.38 grams of zinc per mole of zinc. So moles of zinc cancel. We're in grams of zinc. Now we just have to do the calculation. All right. So 12.5 divided by 36.46 divided by 2, and then multiply by 65.38. And we get 11.21 grams of zinc. So we would need 11.21 grams of zinc to react with 12.5 grams of HCl. And that makes sense because zinc is heavier than HCl, right? So there we go. All right, let's go ahead and do this last page here. I think there's some that after this, you guys should understand all of this stuff and how to do it. Okay, so for the combustion of octane, so C8H18, shown below, use dimensional analysis to solve these problems. All right, so we have C8H18 plus oxygen goes to CO2 plus H2O. All right, so we need to put an 8 in front of CO2 to balance the number of carbons. And now, in order to balance the hydrogens, we need 18. So divide that by 2, that's a 9. So 9 of these guys. So now I have, let's just figure out how much oxygen I have. I have 9 oxygen plus 8 times 2 gives me 25 oxygens. I know I'm not going to really be able to do this right. So that I'm going to say I have 25 halves times 2. So really what I'm going to do here is I'm going to rewrite this equation. I'm going to say 2 C8H18 plus 25 O2 goes to, and then 2. So I'm multiplying everything by 2, right? Basically, I'm going to take this whole thing times 2. So 2 times 8 is 16 CO2 gas plus 18 H2O gas. All right. And that way I get rid of my fraction here. Okay. So how many moles of oxygen are needed to burn 2.786 moles of octane? So we have 2.786 mole of oxygen, of octane, C8H18. So we only need to go from moles of oxygen to moles moles of octane to moles of oxygen, right? Moles of oxygen are needed to burn this many moles of octane. So this is an easier problem than what we were doing on the other page. The first thing we need to do to convert from moles of this to moles of that is use the stoichiometry of this and this. So we want to multiply this by 25 mole O2 for every 2 mole C8H18. And that's the whole problem. So 2.786 times, I don't know if you can see this. Okay, there we go. Times 25 divided by 2 gives me 34.83 mole of oxygen produced or needed. That's how much we need. Okay. Now, how many moles of octane were burned if 285.55 grams of carbon dioxide was produced? Okay, so we're going to now go from mass of carbon dioxide to moles of octane. Okay, so we have 285.55 grams C8, CO2. Um, and now we got to convert from, so here's what we're doing. We're going from um, mass CO2 to moles CO2 to moles of octane, C8H18. Okay. Go from mass to moles. We need the molar mass. So that'd be 1 mole CO2 per, okay. So the molar mass of CO2 is going to be 12.01 for the carbon plus 2 times 16 for the oxygen gives us 44.01 grams. Now we go from mass to moles. Now we got to go from moles of CO2 to moles of octane, right? So this is going to be using the mole ratio of 16 CO2 and 2 octane. So that'd be 2 C8H18 for every 16 CO2. And that's where we stop because it didn't ask us for mass. It only asked us for moles. Don't go too far, right? All right, so then 285.55 divided by 44.01 times 2 divided by 16 gives us 8.110 times 10 to the negative 1. 8.110 times 10 to the negative 1 moles of C8H18. Okay. All right. How many grams of water are formed from the combustion of 500 grams of octane? Okay, so now what we're going to do is we're going to go from mass of C8H18 to moles C8H18 to moles of H2O to mass of H2O. Okay. So to go from mass of octane to moles of octane, we need to use the molar mass of octane. To go from moles of octane to moles of water, we need to use the mole ratio of water to octane. Actually, it should be this one, water here, to octane, right? And then to go from moles of water to mass of water, we need the molar mass of water. So let's go ahead and do this. We have 500.0 grams of C8H18. And we already calculated the molar mass of, oh, didn't we? I guess we never did. So the molar mass of octane is going to be, let's go ahead and write this out. So 1 mole C8H18. All right. So then we have, do it here. There we go. Clear. So that's going to be 8 times carbon, which is 12.01, plus 18 times hydrogen, which is 1.008, gives us 114.22 grams, 114 114.22 grams. Okay. And now we've gone from mass to moles. Now we need to go from moles to moles. This is going to be moles of water. We have 18 moles of water, 18 mole H2O for every 2 moles of octane. So 2 mole octane. And now we want to go from moles of water to mass of water. We need to use the molar mass of water. So it's going to be, we want the moles to cancel out. So that'd be 1 mole H2O. And that's going to be 16 for oxygen plus 1.008 for hydrogen. Oops, clear. So that's going to be actually 16.00 for oxygen plus 2 times 1.008 for water. And that gives us 18.02. 18.02 grams. And there's our calculation. So we went all the way to mass, right? So 500 divided by 114.22 times 18 divided by 2 times 18.02 equals 709.95. 709. Well, we actually only have 4 sig figs, so 709.9. 0.9 grams of water. So how many grams of water are formed from the combustion of 500 grams of octane? 709. That is a lot of water formed, right? All right, very good. So one more problem to go. Let's do this last one here. All right. Suppose you fill up your vehicle with 12.760 gallons of octane. Note that the gasoline actually has a mixture of compounds. So we're just filling it with octane. We're assuming just octane, okay? What is the mass in kilograms? Mass in kilograms of the carbon dioxide that you produce when burning the octane. The density of octane is this. You can calculate the mass in pounds. All right, so we're going to have to use some conversion factors. We're going to have to go from gallons of octane, so C8H18, to mass of octane. No, so from gallons to, I guess we'll call this volume. Volume of octane to mass of octane, C8H18, to moles of octane, C8H18, to moles of carbon dioxide, CO2, to mass of CO2. All right, so first thing to do is we have 12.760 gallons. And now we need to convert from gallons to something that we can use this density on, right? So we need to somehow get to cubic centimeters, but we can convert from gallons, where is it, to liters. Okay, so 1 gallon is equal to 3.785 liters. So 3.785 liters per gallon. And then we can convert from gallons to mils. So 10 to the third ml per liter. And then we can convert to cubic centimeters. So 1 cubic centimeter is 1 ml. And then we can use the density to convert to grams. So times 0.6986 grams per cubic centimeter. So now we've just gone from volume to mass, finally, of octane. Now we need to go to moles of octane. So we can take the molar mass of octane. So that's 1 mole C8H18 per 114.22 grams. Now we just got to moles of octane. Now we need to go to moles of CO2. So there is 16, oops, let's go down here so you can see this. There are 16 CO2s for every 2 octane, okay? So 16 CO2 for every 2 C8H18. And then the last piece, we need to use the molar mass of CO2, which I thought we used. Oh, yeah, there it is. Molar mass of CO2. So that would be 44.01 grams per mole CO2, right? And that will give us mass in grams. Then we have to convert from grams. So that would be 1 kilogram, because it wants it in kilograms, for every 10 to the third grams. Okay. It's kind of a long dimensional analysis, but it does all of our work in one thing. So let's just see that we did it. Okay. Make sure before we do our calculation that we have our dimensional analysis correct. So gallons to gallons, liters to liters, mils to mils, cubic centimeters, grams to grams. Those are octane, or yeah, octane. Then moles of octane, moles of octane, moles of CO2, grams of CO2 to kilograms. All right, so it's all set up there. Let's do our calculation. All right, let's see if we can do this. All right, here we go. Good. Clear. So 12.760 times 3.785. And then times 10 to the third. Oops. There we go. Times 0.6986 divided by 114.22 times 16 divided by 2 times 44.01 divided by 10 to the third equals so 104.0 104.0 kilograms of CO2. Okay. Wow. So there you go. I hope that was helpful for you guys. Let me know what you think. Give me a like, subscribe. Tell me what you'd like to see next. All right, guys. Have a great one, and I'll see you in the next one. Thanks.